Hey everyone! In this video, we'll try to visualize the phenomenon of earthquake shockwaves. Specifically, we'll look at a recent earthquake in California and explore the shockwaves it sent. After a large earthquake, these shockwaves are common, but just how common are they? We'll find out soon. Before we begin our analysis, let's explore the data we have. Our main source of data will come from the earthquake data function, which has some very intuitive syntax. With only a geoposition as its argument, it returns all earthquakes nearby. So if I input the Grand Coulee Dam, which is the largest power generating facility in the US, and apply my earthquake data function on it, I get a list of all nearby earthquakes. Taking the length and a brief glimpse into the data using the span function shows us that there are over 700 earthquakes that happen nearby, and the data is in the form of earthquakes being associated with their properties. Now, what properties does our earthquake data have? I can simply call its properties to find out. As you can see, there's a wide variety of properties we can utilize to help us in our analysis. What about if I only want earthquakes of a certain magnitude? I can simply add a magnitude after my geoposition to indicate that I only want earthquakes stronger than or equal to 4 on the Richter scale, the most common scale used to measure earthquake severity. Mapping the magnitude pure function onto my new data to extract the magnitude properties shows me that indeed all earthquakes have magnitude 4 or greater. I can also put in another constraint, which is a date constraint. Let's say I only want earthquakes from the past month. I can input the range for my dates. In this case, it will be from a month before today to today, and get a new list of earthquakes. Mapping the period pure function onto my data to get the periods of these earthquakes allows me to plot them easily using timeline plot, in which this nice visualization is generated. Let's explore strong earthquakes. For the most part, any earthquake of magnitude 5 or higher can inflict noticeable damage. Let's explore these types of earthquakes. I'll start by retrieving all world earthquakes with such magnitude that occurred in the last 20 years. Mapping the head and dimensions function onto my earthquakes world variable using through gives me that I have an association that is pretty big. The 10 here shows us that with each earthquake there are 10 keys corresponding to the properties returned by the earthquake data function. We can see what this looks like by taking the first element using our double brackets and a span. Let's now consider only magnitudes. I want to look at the frequency of magnitudes and see if there is a relationship. I can do that by taking the values in my data, which gives me each earthquake's properties, and take the magnitude of all of them. I can visualize the distribution using a smooth histogram. Here I am indicating that I want a PDF or probability density function. And it looks like there's an exponential decay relationship going on. What about these earthquakes' geographic distribution? I can take the values of my data and take the position of all the earthquakes in there and then store that into my points variable. Using a geohistogram, I can visualize this data by plotting bins of diameter 500 kilometers and centering my map on the Pacific Ocean. We can also look at geographics, and our conclusion is the same, which is the ring of fire. As seen with volcanoes as well, this ring on the two sides of the Pacific Ocean has a disproportionate amount of earthquakes and volcanoes. Through some basic computational analysis, we just uncovered it. I was curious, what is the strongest earthquake in recent history? I can simply take the maximum of my data using the maximal by function and indicate that I want to look at the magnitude property. I'm using a pure function here as indicated by the green hashtag and ampersand to ensure our maximal by function applies itself properly on our data. We get this earthquake right here, which happened in 2011. We can visualize its location using a geomarker on our previous outputs keys and the geographics function. It looks like it occurred in Japan. This was the most powerful earthquake to be ever recorded there, and it caused huge tsunamis. Let's plot its location with a smaller georange, namely 300 miles, to pinpoint its location more precisely. We see that it occurred near the north coast. This earthquake also caused a nuclear disaster in a nearby nuclear facility called the Fukushima Daiichi Nuclear Power Plant Complex. I was wondering, how close was the earthquake to the site? We can use geodistance applied to our earthquake and the list of nuclear reactors at Fukushima Daiichi and take the minimum to find out. It turns out to be a bit less than 100 miles away. We can also visualize the earthquake's proximity using geographics again with a geodisk surrounding the earthquake center stretching out to the nuclear reactors. Let's move on to California data. I will start by obtaining data for California earthquakes last year above magnitude 2, which is barely noticeable. I can visualize the locations of these earthquakes by plotting a red point on all the positions in my data. We see a concentration here, which is the well-known epicenter of Ridgecrest City. We can also look at our data using a geohistogram by taking the values in our data and taking all their positions. We again see the concentration of earthquakes in Ridgecrest City. I want to touch on another way we can organize our data. This is our data now. It is simply made up of an association of associations. How can we arrange it in such a way that it is readable? Datasets. I can simply apply the dataset function on our data, and then, as you can see here, the data is organized in a nice way with columns and rows identified through a darker gray color. What if we want to plot a geohistogram here with our new format? This simple code does it. I will take my dataset ds and indicate that I want the right composition of the values and geohistogram functions. This right composition is like the function composition you see in an algebra class. I will also indicate that I want the position column. This gives us the exact same plot. Moving on, let's consider the number of earthquakes California sees hourly. Yes, hourly California does see earthquakes. Most of these are barely or not noticeable at all by humans. We'll proceed to take the values in our dataset and take the period, and then we'll group these earthquakes by the hour. Finally, we will take the length in each hour as we only want the frequency. We finish it off by applying the normal function to get rid of the dataset format and then encode our data in a time series. Time series are specialized lists of data in which the x value is a date object and the y value is a number or a quantity. We can take the mean over a time series to get that it's about 3 earthquakes every hour. The /n here, which is a postfix form of applying a function, indicates that we want a numerical answer instead of a fraction. Let's visualize this frequency over the entire year. We'll use the dateless log plot function to plot it, as the log scale will help us visualize it better. Aha, we see a peak in July. This could be due to a large earthquake and its aftershocks. Our visualization is rather hard to interpret though, so instead of looking at the very granular hour, let's consider a moving average of 2 days. Our moving average function basically averages over 2 days by moving along the data and taking the average of our values. I'll plot both of these using the dateless log plot function, and as you can see, we have a much cleaner visualization now. Let's find out if this spike is due to the big earthquake we're thinking about. I'll first take the maximum magnitude in my dataset using the maximal by function. I will extract the properties of this earthquake by taking the values of the row. Plotting it using a geomarker and geographics gives us the same famous location of Ridgecrest City. Let's also visualize where it lies on our previous plot of earthquake frequencies. I can do that by adding an epilogue and indicating I want a large red point at the specific period it occurred. My y value will be the evaluation of the time series at the period the earthquake occurred in. This epilogue option simply serves to overlay additional graphics on any visualization. As we can see, it's right at the peak. Okay, our suspicion is now confirmed. Let's see how this big earthquake affected the area around it. I will first generate my data by taking the earthquake data function, indicating the position I want to consider is that of my big earthquake, and that I want all earthquakes within 1 month of the date of my big earthquake. I can visualize this using the geographics function, and it looks like there are hundreds of earthquakes nearby. Let's explore the data to see how we can visualize the shockwave frequency over time. I'll be applying very similar code here, simply grouping my data's periods by the hour and taking their length and then encoding that data in a time series. I can visualize this time series using dateless plot. As you can see, there are virtually no earthquakes until our big earthquake hit in July, which sent a shockwave inciting even more earthquakes. We can make more sense of this by taking the moving average as we did before. The sharp spike in early July and the decline afterwards effectively shows the shockwaves that ensued due to our big earthquake. I encourage you to explore more about shockwaves, for example, taking the earthquake we looked into in Japan and exploring the shockwaves it sent.